Hello, pre-calculus students, and welcome to our continuing videos on properties of limits. And in this video, we're going to take a look at limits of piecewise functions. And so I have a function here, f of x equals x squared minus 9 divided by x minus 3. And this only applies if, this is just another way of saying if x is not equal to 3. And if x is equal to 3, then f of x equals 2. Okay? So let's do a little bit of background work here. Let's just look at this part. So we know that f of x is equal to, this top part here is x plus 3 times x minus 3. All of that over x minus 3. And again, this only applies when x is not equal to 3. Okay? Well, this cancels and this cancels. The other part, we're just going to leave it alone for now. And so what we have here is a graph of x plus 3 with a hole at x equals 3. So let me just show you what I mean. If I were to graph the original equation, x squared minus 9 divided by, parentheses, x minus 3, let's use my standard window here. You can see here that this graph that it's drawing looks very much just like a line. And in fact, it's defined at all these different places. Okay? However, if I type in 3 for x, you can see here when I type in 3 for x, y is 0, is undefined because there's a hole there. Okay? And so a quick caveat here is if you're not familiar with this, you should look at some of the very early videos, perhaps from chapter 1 or chapter P. But I'm continuing this work here, assuming that you understand how to analyze functions and find where the range and domain and where things are undefined. So we can draw a graph of this function now. So again, this item has a y-intercept at 3, x-intercept at negative 3. And it goes like this. However, when x is actually equal to 3, it's got a hole in it. Now, that's the first part, that's the first piece of this function. The second piece says that f of x is always equal to 2 if x equals 3. So at 3, f of x is actually equal to 2. And this is somewhat of a weird thing, but we can still answer the question for this limit. As x gets closer and closer to 3, as I stand on this graph and I walk along it, I get closer and closer to 6. Okay, this point here is 3, 6. Okay. But of course it's not defined, it's a hole on the graph. But the limit still exists. As you walk along this curve here, you get closer and closer to this point. As x gets closer to 3, f of x gets closer to 6. Okay? And this is true from both directions. If you're coming at it from this direction, you still approach 6. So we know then that the limit of f of x as x approaches 3 is equal to 6. Okay? And this is certainly true. Now, something that's a little bit interesting here is if you just take 3 and you plug it into the function, f of 3. So if you just take 3, you don't get 6 because it's undefined at 6. You get 2. So this is a little bit different than what we've seen before. And so I want to make kind of a note or a caveat or whatever you want to call this. Say that for piecewise functions, f of some number is not always equal to the limit as x approaches some number. Okay? So it could be equal to, but it's not always equal to. In this case, we can see that if you take f of 3, you get 2, but if you take the limit as x approaches 3, you actually end up with 6. Okay? So this problem here serves a couple purposes. First, it is a refresher for how to graph and how to deal with piecewise functions. And second, it shows us how to find the limit of a piecewise function. It's really not a whole lot different like anything else. But the thing that's a little bit different here is that the direct substitution value is not the same thing as the limit. Okay, so, and this is probably one of the more basic and simple piecewise functions. In the next example, we're going to look at some cases where it's a little bit more complicated than this. All right, thank you for watching. Have a wonderful day.